Okay, let's dive right into this explainer and fundamentally rewire your brain to absolutely conquer choice-based algorithmic problems. Look, if you've ever stared blankly at a coding challenge, totally frozen by the sheer number of possibilities, you are in exactly the right place. Today, we are not memorizing syntax. No way. Instead, we are installing a mental framework. Think of me as your personal coach. We're going to train your brain to instantly recognize, visualize, and systematically crush backtracking algorithms just like a seasoned ex-Google interviewer.
So, here's the question. How do you find all the valid combinations of a problem without getting completely lost in some infinite recursive loop? This right here highlights the absolute monster we are fighting today, the overwhelming, computationally terrifying nightmare of brute force search. Just imagine having to generate literally every single permutation of a massive dataset. If you use a naive brute force approach, you are blindly exploring every possible path, even the ones that were completely doomed from step one. We desperately need a way to search intelligently, right?
To build that intuition, we are going to cover 5 key steps. First, moving beyond brute force. Second, visualizing the hidden decision tree. Third, mastering the choose, explore, undo template. Fourth, nailing pattern recognition. And finally, number 5, the expert advantage of pruning. Let's get into it.
Starting off with Section 1, Intuition Beyond Brute Force. It is time to escape the labyrinth of exponential search spaces.
So the crucial point here is comparing standard depth-first search with backtracking. While a standard DFS blindly follows a single path down, down, down until it literally can't anymore, backtracking gives you an explicit superpower, and that superpower is the ability to hit undo. You're building up a partial solution just one step at a time, but the very second that partial solution hits a dead end, boom, you restore your previous state and immediately try something else.
Think of yourself as a hero navigating a massive maze. Instead of blindly running down every single path to the bitter end, which takes forever, right? You make calculated, deliberate steps. If you see a brick wall up ahead, you don't just keep bumping your head against it. You stop, you step back, literally you backtrack, and you turn down a completely different corridor. This controlled exploration is exactly what separates a wildly fast, elegant algorithm from one that just straight up times out.
Moving right along to Section 2, the hidden decision tree. Let's start visualizing your choices.
Here is the secret. Every single combinatorial problem hides a massive decision tree. It's like a giant puzzle. You always start at the very top, the root, with a completely empty state. From there, you branch out by making a single choice. And guess what? Each choice unlocks subsequent choices, pulling you deeper and deeper into the tree. Finally, when you reach the very bottom, what we call the leaf nodes, you check if you found a valid configuration. If you have, awesome. You harvest that solution and keep going.
Which brings us to Section 3, Choose, Explore, Undo. This is the universal 3-step template.
Okay, if you remember one thing from this explainer, make it this. The choose, explore, undo mantra powers almost every single backtracking solution in existence. First, you choose. You commit to a decision and modify your state. Second, you explore. You recursively call your function to dive deeper down the tree. And third, pay close attention, because this is where like 90% of interviewees completely fail. You undo. After that recursive call returns, you absolutely must reverse the decision. You pop it off the list, revert the state, and make sure the next iteration starts completely fresh. Pick, explore, unpick.
Let's watch how this template physically plays out. Imagine a problem where we need to find paths from the upper left to the lower right of a 7x7 grid. And the catch is, we have to visit every single square exactly once. Our algorithm steps forward, chooses a direction, and recursively explores deeper to see if it can reach the end. It's carefully sneaking its way through. But wait, look what happens here. The path has twisted in a way that it actually splits the remaining unvisited squares into 2 completely isolated halves. Because the rules say we must visit every square in a single continuous line, completing this puzzle is now mathematically impossible. The solution is completely doomed. So, we don't waste precious time exploring a doomed path, we immediately trigger our undo step. We'd back up and we try a totally different route.
Now let's hit Section 4, Backtracking Pattern Recognition. These are the trigger words that instantly reveal the algorithm.
In a high-pressure interview, if you read a prompt and see phrases like generate all possible configurations or find all valid arrangements, your brain needs to instinctively classify it as backtracking. I'm talking within the first 30 seconds. Words like combinations, permutations, or mentions of an exponential solution space are massive, flashing neon signs.
They are literally screaming at you to set up your recursive choose, explore, and undo template.
And the beauty is, whether you are placing queens on a chessboard, solving a Sudoku puzzle, or finding words in a grid, the underlying mental engine is exactly the same. In N-Queens, your choice is placing a piece, and your undo is picking it back up. In a word search, your choice is moving to a specific letter, and your undo is unmarking that cell. The context changes, but the framework is absolutely identical.
Finally, we arrive at Section 5, pruning. This is the absolute expert advantage for optimizing the search space.
So what exactly is pruning? Well, by detecting an invalid path early, we just stop exploring doomed branches. Pruning is simply injecting some intelligence into the algorithm so it notices immediately if a partial solution is failing. And here's why it's a total game changer. Every single time you prune a branch near the top of your decision tree, you aren't just saving one single calculation. No way. You are instantly eliminating millions of downstream recursive calls.
To really put that into perspective, let's look at the mathematical shock of pruning on that 7x7 grid problem we talked about earlier. A basic brute force backtracking algorithm took a massive 483 seconds and made 20 billion recursive calls. Yes, billion with a B. But by simply telling the algorithm to prune branches the moment the grid splits into unvisitable sections, the runtime collapses to just 0.6 seconds. The recursive calls drop to 69 million. It's the exact same logic, just slightly more intelligence, and it is literally nearly 1,000 times faster.
Armed with this mental framework of choose, explore, and undo, you really no longer need to fear an exponential search space. By automatically spotting the trigger words, mapping out the hidden decision tree, and aggressively pruning invalid paths, what once seemed like an overwhelming nightmare is now just a systematic checklist. But I'll leave you with this. What happens when even the most perfectly pruned backtracking algorithm is still way too slow, simply because you're calculating the exact same subproblems over and over again? Well, that is the precise moment we upgrade from backtracking to dynamic programming. But for now, what combinatorial problem can possibly stop you?